The equations that describe how atoms move are mathematically unsolvable, proven. For anything more than two particles, your body has 7 octillion atoms. And right now, a computer is simulating a protein made of 50,000 of them and using that simulation to design a drug. On top of math, that has no solution.
And the really good part, we're not even using the real equations. We threw those out. We replaced quantum mechanics with springs, literal springs, and it works well enough to run clinical trials on.
The simulations that cost $400 million to run are based on springs.
Calibrated springs. There's a distinction.
How do you simulate atoms when you can't solve the equation for 3 of them?
You fake it. You fake it across 1 billion time steps and you call it a trajectory.
It is mildly extraordinary that billion-dollar pharmaceutical pipelines rest on approximations that were considered a stopgap in 1927.
I'm calling this Sim Pharmaco, fake physics as a service, subscription tier per molecule. I'll take the deck to Sand Hill on Thursday.
It's like guessing what the soup will taste like by stirring it.
Patar, that is not helpful right now.
Stop! Here's the actual problem. Newton's equations of motion, force equals mass times acceleration, are analytically unsolvable for more than 2 interacting bodies. Poincaré proved this in 1890. The 3-body problem has no closed-form solution. Your average drug target is a protein with 15,000 atoms floating in a box of 30,000 water molecules. GROMACS simulates it anyway, not by solving the equations, but by approximating them, femtosecond by femtosecond for long enough that biology happens. By the end of this episode, you will understand exactly how that approximation works, where the Born-Oppenheimer Approximation lets us throw out quantum mechanics, why the 3-body problem makes all of this necessary, and why the drug discovery pipeline has been failing for 2 decades because we treated a breathing, shifting protein like a statue. Let's go.
I'm Bobby Sponge, and I feel like I already need a moment.
I'm Dr. Silly. I will do my best not to make this feel like a numerical methods course.
Kelpie. I have GROMACS running on a cluster in my shed. It has been running for 12 days. I have stopped checking what it's doing.
Crabzilla. I have investments in 2 computational drug discovery startups and 1 QMMM SaaS company. I will be doing due diligence throughout this episode.
Squiven. I note the distinction between simulation and reality will be relevant.
Patar.
If you understand protein dynamics well enough to tell someone why their rigid docking pipeline is going to fail, you are ready to subscribe to this channel. If you do not understand that yet, subscribe, because you will by the end. The button is there. GROMACS is watching. It has been running for 12 days, and it has seen things.
Let's start with the fundamental problem. You want to simulate how a protein moves through time. To do that, you calculate the force on every atom, then use Newton's second law, force equals mass times acceleration, to update every atom's position and velocity. Simple in principle.
Okay, so far, what's wrong with it?
Every atom exerts a force on every other atom simultaneously. The force between any 2 atoms depends on their relative positions, their charges, and their identities. For a system of n atoms, you have n times n minus 1 divided by 2 unique pairwise interactions. For 15,000 protein atoms plus 30,000 water molecules, that is roughly 1 billion pairwise interactions per time step.
And a time step is how long?
2 femtoseconds, 10 to the minus 15 seconds. To simulate 1 microsecond of biology, you need 500 million time steps, each with approximately 1 billion interactions.
So it is very approximately 5 times 10 to the 17th operations per microsecond of simulation, which is why the people who run Anton for a living have a cooling bill that could fund a small nation.
I see a compute arbitrage angle here. Anyone else? Cloud Native MD, paper femtosecond. I would call it femtocloud.
That name is mildly terrible and will almost certainly succeed.
But here's the deeper problem, and it's why we're talking about the 3-body problem on a biology podcast. In 1890, Henri Poincaré proved that for 3 or more bodies interacting gravitationally or electrostatically, the math is equivalent. There is no closed-form analytical solution. The 2-body problem has one. Earth orbiting the sun produces a perfect ellipse. You write down a formula, plug in time, get position. The 3-body problem, no such formula exists. The solution is chaotic. It is sensitive to initial conditions. It can only be approximated numerically.
So 3 atoms, no formula, 15,000 atoms.
You have 15,000 instances of the three-body problem, all coupled to each other, simultaneously. And you are running it for 500 million time steps. This is why molecular dynamics exists as a discipline.
And the solution is just do it step by step, brute force.
That is precisely what molecular dynamics is. We cannot solve the equations, so we iterate. Every 2 femtoseconds, calculate forces, update velocities, update positions, repeat. Numerical integration instead of analytical solution. We give up exactness and get approximation in exchange.
Like counting steps instead of looking at a map.
Yes, actually, that is closer than usual, Patar.
It is?
If you can't describe where you'll be in an hour analytically, you walk the path one step at a time and see where you end up. That is molecular dynamics.
Now, to calculate the forces between atoms, you actually need quantum mechanics. The force between 2 atoms is determined by their electron clouds, the wave functions of their electrons interacting. The correct equation is the Schrödinger equation, Hp psi equals Epsi. The Hamiltonian contains terms for kinetic energy of every electron, kinetic energy of every nucleus, electron-electron repulsion, nucleus-nucleus repulsion, and electron-nucleus attraction, all coupled together.
And we can solve that?
For hydrogen, 1 proton, 1 electron. Yes, exactly. For helium, 2 electrons. We already need approximations. For a protein with 5,000 electrons, solving the full Schrödinger equation exactly is computationally impossible, not slow, impossible with any hardware that will ever exist.
So, what do we do?
We throw most of it away elegantly.
In 1927, Max Born and J. Robert Oppenheimer published the Born-Oppenheimer Approximation. The key physical insight: nuclei are approximately 1836 times heavier than electrons. A proton is 1836 times heavier than an electron. Because nuclei are so much more massive, they move orders of magnitude more slowly. From the perspective of the electrons, the nuclei are essentially stationary. The electrons adjust their wave function instantaneously as nuclei move.
So they're on different timescales.
Completely different timescales. And this means we can decouple them. We solve the electronic Schrödinger equation independently for any fixed nuclear geometry. The result is the potential energy, the energy of the system as a function of nuclear positions. This gives us a potential energy surface, a landscape where every point represents a nuclear configuration and the height represents its energy.
And then the nuclei
move on that landscape, like balls rolling on a surface. They follow the gradient, the force, determined by the electronic energy. We've reduced a fully quantum problem to a classical one for the nuclei, with quantum mechanics providing the landscape they move on.
And then we throw away the quantum mechanics for the landscape, too.
I'm sorry. We throw away the quantum mechanics as well.
We replace the quantum potential energy surface with a parameterized empirical function. A force field. Bonds are springs. Angles are springs. Dihedral torsions are cosine functions. Van der Waals interactions are a Leonard-Jones 12-to-6 potential, a well that goes sharply repulsive at short range and has a weak attractive minimum at the equilibrium contact distance. Electrostatics are Coulomb's law, with fixed partial charges on each atom.
Curated springs. That's the product. I'm writing the pitch deck right now.
The parameters: spring constants, equilibrium lengths, partial charges, Leonard-Jones radii, are fit against experimental observables and high-level quantum mechanical calculations on small molecules. Amber, charm, gromos, these are our force fields, decades of careful parameterization, encoding the best quantum-derived physics into a form that a computer can evaluate in microseconds rather than years.
So we went from Schrödinger equation and to Born-Oppenheimer approximation to a parameterized set of springs, and then we run GROMACS.
Which is sitting in my shed running a membrane protein simulation that has been going since last Tuesday.
Let's walk through what GROMACS actually does. You start with a protein structure, typically from X-ray crystallography or cryo-EM downloaded from the protein databank. You place it in a simulation box filled with explicit water molecules. You assign force field parameters to every atom. Then you run the loop.
Walk me through the loop.
Step 1, calculate forces. For bonded terms, bonds, angles, dihedrals, you evaluate the force field functions. For non-bonded terms, within a cutoff distance, typically 12 angstroms, you calculate van der Waals and electrostatic forces directly. For long-range electrostatics beyond the cutoff, GROMACS uses particle mesh ULD, PME. The long-range electrostatic sum is decomposed into a short-range real space component that decays quickly and a long-range reciprocal space component computed by a fast Fourier transform. This reduces the scaling from order n squared to order n log n.
I understood faster.
N log n versus n squared is a meaningful cost reduction at scale. That is the difference between a viable SAS and a cost center.
Step 2. Integrate. GROMACS defaults to the leapfrog Verlet integrator. Positions are calculated at integer time steps. Velocities are calculated at half-integer time steps. They literally leap over each other in alternating sequence. This makes the integrator time reversible, which is necessary for Hamiltonian dynamics and keeps energy conserved over long trajectories.
Time reversible meaning you could run the simulation backward?
Exactly. A non-time reversible integrator like forward Euler accumulates systematic error. Energy drifts, the simulation slowly heats up or collapses. The leapfrog Verlet integrator is stable for very long simulations because energy is conserved by construction.
Step 3. Constraints. Bonds involving hydrogen, which vibrate at extremely high frequency, are constrained to fixed lengths using the Links algorithm. If you try to simulate hydrogen bond vibrations explicitly, your time step has to be half a femtosecond. Links freezes those bonds, and your time step jumps to 2 femtoseconds, 4 times the simulation length for the same compute cost.
Just freeze the hydrogen bonds and go 4 times faster? Why doesn't everyone do that?
Everyone does.
Step 4. Thermostats and barostats. Real biology happens at constant temperature and pressure, not constant energy. GROMACS applies velocity rescaling thermostats and Perinello-Raman barostats to maintain the desired ensemble, and the box has no walls. Periodic boundary conditions mean that when a molecule exits one face of the box, it enters through the opposite face. This simulates a small piece of bulk solvent without edge effects.
The box has no inside.
That is geometrically accurate and mildly unsettling.
The box has no inside. I'm going to think about that for a week.
And now do that loop. Calculate forces, leapfrog integrate, apply constraints, apply thermostat. Every 2 femtoseconds for 500 million steps on a GPU cluster. With CUDA acceleration in the PME and force calculation inner loops, a modern A100 gives you roughly a microsecond of simulation per day for a medium-sized protein.
Is a microsecond enough?
Microseconds are where interesting biology starts. Sidechain rotamers equilibrate in tens of nanoseconds. Loop motions, hundreds of nanoseconds to microseconds. Helix rearrangements, domain motions, ligand binding events, microseconds to milliseconds. Below a microsecond, you're mostly watching vibrations. At a microsecond, you're starting to see the protein actually do something.
Which brings us directly to where the simulation methodology starts to matter for drug discovery, because the biology that happens at microsecond timescales breaks an assumption we've been making since the field began. Molecular docking is the computational approach to predicting how a small molecule, a drug candidate, binds to a protein target. The classical method, the protein is held rigid, fixed in its crystal structure geometry, and the ligand is flexible. Its rotatable bonds are sampled, and docking scores the pose by estimated binding affinity. Autodock vena glide in standard precision. This is what most of the field has been doing since the 90s.
What's wrong with that?
Proteins are not rigid. A crystal structure is one snapshot, one local minimum in a vast conformational landscape. At physiological temperature, proteins breathe. Side chains rotate, loops shift, active site geometry changes. The binding pocket you're docking into in the crystal structure may not look anything like the binding pocket that exists when a drug actually arrives.
So we've been doing drug design by taking a single photo of a protein and trying to slot a molecule into the photo?
That is not an unfair description of 2 decades of computational drug discovery.
And this is why I run ensemble docking. You generate 100 or 200 protein conformations from your MD simulation, different snapshots spread across the conformational distribution, and you dock your ligand into all of them. Instead of one rigid crystal structure, you're exploring the entire thermally accessible shape space of the protein.
That takes 100 times as long.
At least. Which is why pharma companies didn't do it while patents were expiring. But compute is cheap now. This argument is over.
It is mildly ironic that the computationally correct approach was commercially unviable for 20 years and is now simply the correct approach.
Beyond ensemble docking, there is induced fit docking, which explicitly models the protein changing conformation in response to the incoming ligand. As the drug candidate arrives at the binding site, the surrounding side chains and loop regions are allowed to minimize around it. Schrodinger's glide with induced fit correction is the commercial implementation. You get a protein geometry that has adapted to accommodate the specific ligand.
That's how it actually works in biology, right? The protein adjusts to the ligand?
Frequently, yes. This is the induced fit model of binding, first proposed by Daniel Koshland in 1958. The lock and key model, rigid protein, perfectly matched ligand, is an approximation that fails for many important drug targets.
And then there are cryptic binding sites. This is where it gets genuinely exciting. A cryptic site is a binding pocket that doesn't exist in any available crystal structure. It is not in the PDB, you cannot see it. It appears transiently during molecular dynamics. The protein undergoes a conformational excursion. A pocket opens up for nanoseconds or microseconds, and if the right molecule is there, it can bind.
Wait, ghost pockets? The protein has ghost pockets that appear and disappear?
Constantly, and some of them are druggable. KRAS G12C, the most important cancer mutation in the last decade, was considered undruggable for 30 years. The oncogenic form of KRAS had no obvious binding pocket. Then MD simulations revealed a cryptic allosteric pocket that appears transiently in the GDP-bound state. That pocket is now the target of sotorasib and adagrasib, which are approved drugs. Cryptic site, MD simulation, real drugs.
MD simulation found a pocket nobody knew existed, and now there are approved drugs from it?
Welcome to where the field is going.
I invested in a company doing exactly this for GPCRs last year, 12 million Series A. The pitch was, we find pockets nobody else can see. I thought it was a metaphor.
It was not a metaphor.
To find cryptic sites, you need enhanced sampling. Standard MD spends most of its time trapped in energy minima. The protein stays near its equilibrium conformation because thermal fluctuations rarely have enough energy to cross barriers into new conformational states. Metadynamics addresses this by adding a history-dependent biasing potential to the simulation. Every time the protein visits a particular conformation, you add a small Gaussian potential to fill up that energy well. The protein is progressively pushed away from states it has already visited, forcing it to explore new regions of conformational space. You reconstruct the unbiased free energy surface after the fact.
So you're essentially bribing the protein into exploring?
The simulation. You're bribing the simulation. The protein doesn't know.
Right, obviously.
For lead optimization, once you have a drug candidate and want to improve it, the most quantitatively rigorous approach is free energy perturbation. FEP, you want to know, does this modified version of the molecule bind more tightly than the original? FEP answers this by simulating the alchemical transformation of one molecule into the other, literally mutating the drug in the simulation, one parameter, step at a time, while measuring the thermodynamic work done. From the work distribution, you calculate the relative binding free energy.
You mutate the drug while it's sitting in the protein?
In the simulation, you add a lambda parameter that interpolates the force field from molecule A to molecule B. You run many short simulations at intermediate lambda values, collect the energy differences, and apply the Bennett acceptance ratio or thermodynamic integration to get the binding affinity difference. Accurate to within roughly half a kilocalorie per mole in well-behaved systems. 1 kilocalorie per mole corresponds to an order of magnitude change in binding affinity.
This is why D. Shaw Research built Anton. Custom supercomputer, hundreds of millions in hardware, built specifically to run FEPI and long-time scale MD fast enough to be useful in a drug discovery cycle.
David Shaw, Renaissance Technologies, quant hedge fund for 20 years. Then he built a biology supercomputer, and the biology people basically had to accept that they needed a hedge fund manager's compute infrastructure to do their jobs. I find this professionally inspiring.
Where are the force fields breaking down, though? You said earlier they fail in silent, dangerous ways.
Force fields are parameterized on small organic molecules in standard chemical environments. When you push them outside that regime, metalloenzymes with zinc or iron active sites where electron density is unusual, covalent bond formation or breaking, exotic post-translational modifications, they fail. Silently. The simulation runs. The trajectories look physically reasonable. The predicted binding affinity is wrong by 2 or 3 kilocalories per mole. That is a 1,000-fold error in binding affinity. The compound you optimized computationally doesn't work in the assay.
And you would never know from the simulation output.
Unless you knew to validate it, no.
Which is why QMMM exists. Quantum mechanics/molecular mechanics. You partition the system. The reactive region, the active site, the metal center, the bond being formed or broken, is treated with density functional theory or semi-empirical quantum methods like GFN2XTB. The rest of the system, the surrounding protein, the solvent, uses a classical force field. The two regions are coupled via electrostatic embedding. The quantum region sees the classical point charges of the surrounding environment, which polarize the wave function correctly.
You run 2 different physics simultaneously on the same system?
On different spatial regions of the same system. Simultaneously. It's computationally expensive, maybe 50 to 100 times slower than pure MD. But you get quantum mechanical accuracy where you need it without paying the full quantum cost for 40,000 water molecules.
QMMM as a service. This is the next layer of the stack. You bill for the quantum region atoms separately. Premium tier.
And beyond QMMM, machine learning force fields are changing the equation entirely. Instead of parameterizing springs by hand, you train a neural network on quantum mechanical data. Energies and forces calculated at the DFT level for thousands of small configurations, and the network learns to predict forces with a near quantum accuracy at a cost close to classical force fields. MACE, NEQUIP, ANI. These models are now achieving sub-kilocalorie per mole accuracy on drug-like molecule benchmarks without any system-specific parameterization.
When I run MESOF23 on my shed cluster with the protein ligand benchmark set from the Merck-FEP benchmark, I get binding affinity predictions that rival the best-tuned classical FAP pipelines. No atom typing, no charge fitting, just a model that learned physics from first principles.
So instead of curated springs, the neural network learned what the springs should do from actual quantum mechanics?
That is an accurate one-sentence description of machine learning force fields.
The force field parameterization services business is going to be disrupted. I know 2 startups it will affect. I have already rescheduled calls with them.
You taught the computer what the soup should taste like. Now it stirs itself.
Patar, that's a callback to your own analogy from earlier. Was that intentional?
The soup is consistent.
Okay, we've done it. We've gone from unsolvable physics to GROMACS to ghost pockets to machine learning atoms. I feel like I need the single sentence version. Patar, go.
Patar, could you summarize what molecular simulation is and why non-rigid docking matters?
You can't write down the answer for how atoms move, so you follow them one tiny step at a time, using close enough rules for how they push each other, rules we got from quantum mechanics and then simplified. You run the clock forward long enough to see what the molecule actually does, and what it does is breathe. The protein isn't a lock. It's a building that shifts and settles. Some doors only open sometimes. You have to watch long enough to see which doors there are and when they open. That's where the drugs are. Behind the doors, nobody photographed.
Patar, what, this whole time you understood the entire episode?
The soup was good today?
I am going to need a moment.
That was the clearest description of molecular dynamics and cryptic site docking I have heard at this table. I will be thinking about it.
I'm going to check on my cluster. It's been 12 days. Something might have finished.
It is mildly poetic that the most accurate summary of an unsolvable problem arrived as a metaphor about a building with occasional doors.
Okay, final exam. We are doing the quiz. 3 questions. Right now. Get a pen.
Or pause the video. I don't care how you take notes. Just take them.
Pause the video now. 3 questions. First, the Born-Oppenheimer Approximation decouples 2 types of motion in a molecular system. What are they, and what physical property makes the decoupling valid? Second, classical molecular docking treats the protein as rigid and frequently fails. Name one approach that addresses this limitation and describe what it does differently. Third, GROMACS uses particle mesh UOLD for electrostatic calculations. What computational problem does PME solve, and what is the scaling improvement over direct pairwise summation?
Pause. Write your answers. Take as long as you need.
I will be running a brief metadynamics analysis while you think.
Okay. Answers. Question 1. Born-Oppenheimer decouples. I said electronic motion and nuclear motion. Valid because nuclei are way heavier, so electrons move way faster. Is that right?
Correct. The Born-Oppenheimer approximation decouples electronic and nuclear motion. The physical basis is that protons, and by extension, nuclei, are approximately 1836 times heavier than electrons. Because of this mass difference, electrons move on a timescale orders of magnitude faster than nuclei. From the nuclear perspective, the electrons adjust instantaneously to any nuclear configuration. This allows us to solve the electronic Schrödinger equation for fixed nuclear positions, producing a potential energy surface on which the nuclei then move as classical particles.
1 for 1.
I wrote the supply side and the demand side. I stand by this as a structural analogy,
It is structurally wrong.
structurally inspired.
Question 2. I wrote ensemble docking. You use multiple protein conformations from MD instead of one crystal structure, so you're not stuck with a single snapshot. Is that right?
That is correct. Ensemble docking generates a set of protein conformations by sampling from a molecular dynamics trajectory, different snapshots capturing the protein's thermal conformational distribution, and docks the ligand into each one. This captures the flexibility the protein exhibits in solution and allows you to find binding poses in conformations that the crystal structure alone would never reveal. Induced fit docking is also an acceptable answer. It explicitly allows the protein to reorganize around the docked ligand, modeling the conformational change that occurs upon binding. Both address the rigidity failure of classical docking.
2 for 2. I cannot believe this is happening to me.
I answered metadynamics to excavate cryptic allosteric pockets. Then FF on the ensemble. Technically a more complete answer. I will not apologize.
I answered hire a better computational chemist, which is operationally correct and strategically valid.
The operational correctness of outsourcing the problem is mildly indistinguishable from solving it.
Question 3. PME. I wrote PME solves the long-range electrostatics problem because computing all pairwise interactions is n squared, which is too slow. PME makes it n log n using Fourier transforms. Is that the right answer?
Exactly right. Direct pairwise summation of electrostatic interactions scales as order n squared. For 50,000 atoms, that is over a billion pairwise calculations per time step, which makes long simulations computationally intractable. Particle mesh UOLD decomposes the electrostatic sum into two parts: a short-range real space sum that decays quickly and is evaluated directly up to a cutoff, and a long-range reciprocal space sum that captures the remaining contribution and is computed via fast Fourier transform on a mesh. The combined scaling is order n log n, which enables the simulation of large biological systems on practical timescales.
3 for 3. I understood molecular dynamics. This is the best day of my life.
The Fourier transform was invented in 1822 by Joseph Fourier to describe heat flow. It is currently one of the most important tools in drug discovery. History is a long game.
I got 1 out of 3 on the quiz, but I understand the investment thesis completely. That is the appropriate division of cognitive labor.
The quiz results are consistent with each individual's demonstrated epistemic approach throughout the episode.
The n-body problem is unsolvable. We approximate it femtosecond by femtosecond, and when we run long enough, we see biology happen. That is molecular simulation.
Subscribe. Because Pitar understood this whole episode the entire time.